Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks, section 13.1. This is an introduction to graphs. Now, you've already seen graphs before actually. They were called digraphs or directed graphs, right? You had vertices and edges that were arrows, and if an arrow pointed from one vertex to another, that meant that they were in a relationship somehow, right? There was some sort of ordered pair. Well, here we're going to look at undirected graphs, right? So the edges between vertices are not going to be arrows, but just segments. All right. So graphs are fundamental objects in discrete mathematics that model relationships between pairs of objects. Graphs arise in a wide array of disciplines, but play an especially important role in computer science. Directed graphs were introduced in the context of relations, right? As I mentioned, you have seen directed graphs before. Here, in this chapter, we are concerned with undirected graphs. In an undirected graph, the edges are unordered pairs of vertices. Right? So just a set of vertices. You're going to be using, little curly braces instead of parentheses, right? Because remember, parentheses means the order matters, But we'll have braces here to indicate that the order doesn't matter. If you have a pair of vertices, that just means that there's an edge between them, no arrows, no direction, no order. And this is useful for modeling relationships that are symmetric. For example, an undirected graph could be used to model sibling relationships within a family, because that's definitely a symmetric relationship, right? If A is the sibling of B, B is going to be the sibling of A. So rather than draw an arrow going back and forth between them, I'll just draw one segment, one undirected segment to connect them. So unlike parent-child relationships, right, in which the two people have different roles, sibling relationships are symmetric. So a graph, right, an undirected graph, we'll see later, consists of a pair of sets, a set V and a set E, where V is the set of vertices, right, they're like points, and E is a set of edges. A graph is finite if the vertex set is finite. So this material will only be concerned with finite graphs, right? So we're not going to see any infinite graphs here, any vertex sets with infinitely many points in it. A single element of V is called a vertex and is usually represented pictorially by a dot with a label, right? And again, you've seen graphs before, directed graphs. So like on this picture, for example, the vertices are A, B, C, D, and E. Each edge in set E is a set itself. So every edge is a set of two vertices from V that are connected by a segment, right? Just a line, no arrows. So in the graph below, again, the vertex set is the set with elements A, B, C, D, E, and the edge set, as they're showing me here, is a set with sets in it. And each set has two elements, and those two elements are in a set if there's an edge between them, a connection. So you see the set with A and B because there's a connection, a segment between A and B. The set with A and C because there's a segment from A to C and C to A, right? So again, they're using the braces here because order doesn't matter. So B to C, there's a segment. B and E, there's a segment. C and D, there's a segment. and D and E, there's a segment, right? So there are 6 edges and 5 vertices. So like I said, curly braces are used to denote the vertices participating in an edge. Recall that curly braces denote a set in which the order of the elements does not matter. In an undirected graph, there is no particular direction to an edge. So the edge with the set, the set A and B is the same as the edge with the set, B and A. They're the same thing, same set. But remember, when we saw directed graphs earlier, an edge in a directed graph was an ordered pair with parentheses because it mattered. Right? In a directed graph, the ordered pair A comma B meant there was an arrow going from A to B. And the ordered pair B comma A would be the other way around, a totally different edge. Right? So directed edges are much looser. And directed edges, had order mattering. A graph may appear to be disconnected into more than one piece, but is still considered to be one graph. It is also possible for a graph to have no edges at all. The diagram below shows 2 graphs whose vertex set is A, B, C, D, E, all the points. The edge set for the graph on the left is with the set A and B, C and D, and D and E. Right? 3 edges in this one graph. Again, it can be broken into, it looks like it's broken into pieces, but it's still considered a single graph. The edge set for the right graph is, the empty set. Right, that circle with a slash to it, as there are no edges. Alright, so for example, it says use the 3 graphs below. All of them have the same vertex set, A, B, C, D, right, the points A, B, C, D. And this is a pretty simple thing, I'm hoping. Right, just match the edge set to each corresponding graph. So let's look at this set, graph A here. I've got the edge AB, so the set AB in there. Got BC, this has BC. Got CD, this has CD. And I've got BD, this has AD, so that's not that one. It's got to be this one, right, with AB, BC, CD, and BD. So this here is the edge set for the first graph. And these are pretty simple. I really hope that they are simple for you. I'll leave the other 2 for you. Alright, so some more definitions. This whole first introductory section is just a lot of definitions. Alright, so parallel edges are multiple edges between the same pair of vertices. So like you see in this graph here, see between vertices A and B, see how there are 2 edges? These edges would be called parallel edges. So there are multiple edges between the same pair of vertices. And they're giving you an example here. Right? Imagine a graph whose vertex set is a set of cities and whose edges are roads connecting pairs of cities. It is possible for there to be 2 or more roads between the same cities, the same 2 cities. So then those would be called parallel edges. In defining graphs with parallel edges, it would be important to have an additional label besides the 2 endpoints to specify an edge in order to distinguish between different parallel edges. So for instance, something that you might want to introduce, maybe call this number 1 and this number 2, or color this edge red and this edge green. So you can definitely tell the difference between the edges that go between A and B. We've seen these before, but again, this will be without arrows, undirected. A graph can also have a self loop, right, which is an edge between a vertex and itself. So you see the self loop here on vertex C. Now, a graph that doesn't have these, Right? If a graph does not have parallel edges or self-loops, it is said to be a simple graph. Right? So this graph up here is not a simple graph because it has parallel edges. Right? It has a self-loop. So unless otherwise specified, an undirected graph in this material is assumed to be a simple graph, right? So they're saying here most of the graphs, unless I say otherwise, most of the graphs we're going to be coming across, we're going to be studying, will not have parallel edges or self-loops. All right, so some more terminology, graph terminology. All right, so here are some definitions for some common graph terms, and they are illustrated with respect to this graph below. So, first definition. If there is an edge between two vertices, then those vertices are said to be adjacent. So see, A and B are adjacent, A and C are adjacent, B and C are adjacent, B and E are adjacent, C and D are adjacent, and D and E are adjacent. Right? So yeah, they give examples. And then, B and D are not adjacent because there's no edge between them. Another definition. Vertices B and E are the endpoints of edge BE. Hopefully that makes sense. They're the points at the ends of the edge. And the edge BE is incident to those endpoints. Right? They would say that, so this edge is incident to vertices B and E. This edge here is incident to vertices A and B. This edge here is incident to vertices B and C, and so on. Another definition. A vertex C is a neighbor of vertex B if and only if the edge BC is an edge. So they're saying here, in the graph above, the neighbors of B are vertices A, C, and E. See, B has an edge to A, an edge to E, and an edge to C. So the neighbors of a vertex are just all the other vertices that vertex is adjacent to. So the neighbors of D would be E and C. All right, the neighbors of A would be B and C, and so on. In a simple graph, the degree of a vertex is the number of neighbors it has. So just basically the number of lines coming off of it, right? The number of vertices it's adjacent to. So for example, if I was looking at vertex A, and I said, what's the degree of vertex A? Well, its neighbors are B and C, that's 2. So the degree of A is 2. The degree of B is 3. Right? There are 3 lines coming off of B, 3 neighbors. The degree of C is also 3, right? B, A, and D. The degree of D is 2. E and C are its neighbors. And finally, the degree of E is also 2. Right? B and D are its neighbors. Very easy to talk about degree. And this is similar to in degree and out degree for a directed graph, right? But you're not worrying about things going in or out this time. The total degree of a graph is the sum of the degrees of all the vertices. So 2 plus 3 plus 3, so far that's 8, plus 2 is 10, plus 2 is 12, and they're doing that down here. So for this graph, the total degree is 12. Right. And more definitions. In a regular graph, all the vertices have the same degree. So this graph here is not a regular graph, because there are some vertices with different degrees, right? This has degree 2, and vertex B has degree 3. And to add to this, something similar, in a d-regular graph, all the vertices have degree d. So if every vertex had degree 2, for instance, that would be called a 2-regular graph. If all the vertices had degree 3, it would be called a 3-regular graph, and so on. Like I said, though, this is not a regular graph, so it can't be some sort of d-regular graph, right? It's not a 2-regular graph because not all the vertices have degree 2. It's not a 3-regular graph because not all the vertices have degree 3. Right. Then here is an example of a 3-regular graph. Every single vertex, all 8 of these vertices, all 8 points, have 3 lines coming off of it. 3 neighbors. Every single point has degree 3. Okay. Now, another definition. Right, lots of definitions in this first section. All right, so a graph H, which has a vertex set called VH and an edge set called EH, is a subgraph of another graph G, which has vertex set VG and edge set EG, if the vertex set of H is a subset of the vertex set of G, and the edge set of H is a subset of the edge set of G. So note that any graph is a subgraph of itself, right? Because remember, every set is a subset of itself. So every graph is a subgraph of itself. All right, so I'm actually going to draw this one and show you what this means, right? They show you, see, H here is a subgraph of graph G. All right, so here I have drawn, graph H, graph G. Now the vertex set of graph H, which I'll call VH, is the set of the vertices in graph, that's A, B, C, D. And the vertex set of graph G is, the set of its vertices, which are A, B, C, D, and E. Right, so that's one part of this, right? You see that the vertex set of H is a subset of the vertex set of G. All right, but on top of that, in order to be considered a subgraph, not only do the vertex, does the vertex set have to be a subset, but the edge set also has to be a subset. All right, so the edge set of H is the set with edges. Well, there's an edge from between A and B. Right, so I got this set with A and B in it here. Other braces, and then AC and CD. That's it, right? Just those 3 edges, and we close this up. And now the edge set of graph G has, edge AB, edge AC. I'm done with A, and then we got B. Now I don't need to do BA because I already got AB. So I'll just do BC and BE. And I'm done with the B's, and then C. Now I've already done BC, so I don't need to do CB. I've already done AC, so I don't need to write CA. Just need CD. And then I'm done with C. Then D, I don't need to do DC, but DE. And that's really it, because now I'm done with D. Move over to E. I did DE already. I did BE already. Right? So there's your 6 edges. Right? And look, every single edge in graph H is also in the edge set of graph G, right? This edge is here, this edge is here, this edge is here, right? So the edge set of H is a subset of the edge set of G. And again, if both of these things are happening, what they would say then is that H is a subgraph of graph G. Right? Now, another thing you could have also done without writing all these sets is basically, can you, if they want to say, hey, is H a subgraph of G, you might ask, can I make all the connections in H in G? So say I got A to B here, well, there's A to B there. Great. Got A to C here, there's A to C there. There is an edge. Wonderful. I got C to D in this, C to D here. Wonderful. Look, do you see how I kind of put the red graph into the blue one? Right? The red graph is a subgraph, part of the blue one. Right? The graph H is a subgraph of G. So you could do that as well. Right? And if you find connections up here that aren't in here, then then H wouldn't be a subgraph. All right. And then they go through another couple examples here. So again, you got 1, 2, A, B, C, D, E, F. 6 vertices. And look, they say they're just going over different definitions of regular and junk. This graph is not regular, right? The degree of A is 1, but the degree of B is 3. The degree of C is 4. So not all the vertices have the same degree, so it's not regular. This graph here, which we'll see is called a cycle, right, for obvious reasons, I'm hoping. This graph is regular. Right? Every single vertex has degree 2, so they'd call it 2 regular. This graph down here might be a little harder to see with all these, but this graph is 4 regular. Every single vertex has 4 lines coming off of it, 4 neighbors. All right. So another graph. So again, questions below, refer to this graph here with 5 vertices, A, B, C, D, E, and there's, edge 1, 2, 3, 4, 5, there's 6 edges. Right? 6 edges, 5 vertices. Is vertex C adjacent to vertex E? Remember, this means that there's an edge between them. Well, is there an edge from C to E? No, there is not. So no. What is the degree of vertex D? How many neighbors does D have? Well, C, B, and E. 3 lines coming off of it. The degree of D is 3. Is the graph a regular graph? Well, I just said the degree of D was 3. Look at C. The degree of C is 2. That's not the same. The degree of A is 1. So no, this is not a regular graph, right? In a regular graph, every vertex has the same degree. Is it correct to say that vertices D and E are incident? No. Remember the definition of incident. An edge is incident to vertices. You don't say that 2 vertices are incident. You say that an edge is incident to 2 vertices. So you might think, oh, D and E, hey, there's an edge between them, sure. But that just means D and E. You could say D and E are adjacent, or you would say the edge DE is incident to vertex D and vertex E. So you can't say that two vertices are incident, so it's not correct to say that. Right. Again, an edge is incident to a vertex. You can't have a vertex incident to another vertex. An edge has to be incident to a vertex. What is the total degree of the graph? Well, let's see. 1 plus 4 is 5, plus 2 is 7, plus 3 is 10, plus 2 is 12. So just going around all the vertices, adding up their degrees, gives me the total degree of the graph. Is the following graph a subgraph of the graph above? Right, so they have this V prime with B, C, and E. Well, let's say B, C, and E, that is a subset of these vertices, so far so good. And E prime, the edges, is B, C, and B, E. Are B, C, and B, E up here? B, C, B, E? Yeah, totally. So the vertex set is a subset of this vertex set, and the edge set is a subset of this edge set. So yes, the graph they just described is a subgraph of the graph we were given. Just again, just working with definitions. All right. Now this field of graph theory, right, studying these structures, these graphs, is called graph theory. Seeks to understand the properties of graphs. Facts about graphs are useful in computer science because they help in designating efficient algorithms that operate on graphs. The following theorem below is a simple fact, a very simple fact, about undirected graphs. And the proof uses induction, as is common in proofs related to graphs. Remember proofs by mathematical induction. Typically, an inductive proof on a graph uses induction on the number of vertices or the number of edges. So, the proof below uses induction on the number of edges. The inductive step, right, assumes that the theorem holds for graphs with m edges and proves that it holds for graphs with m plus 1 edges, right? You've seen proofs by induction before. This should be familiar. It's just, working with these graphs now. All right, so here it is. Theorem, a simple property about, simple undirected graphs. If G is an undirected graph, then twice the number of edges will be equal to the total degree. So remember that total degree. Here's an example up here, right? Number 5. When I was asked about the total degree of this graph, well, instead of what that theorem is saying is that instead of adding up the degrees of all the vertices, which gave me 12, you can just count the number of edges and double it. So there were 1, 2, 3, 4, 5, 6 edges. Double that is 12, and that will be the same as the total degree of the graph. Right, and you could also then use this theorem to help you find the number of edges. Right, if you know the total degree, just divide by 2, and you'll get the number of edges. Right, very nice result. And I will let you read the proof. Right, it's a very nice proof, a proof by mathematical induction on the number of edges. Right. All right. So for example here, some use of the theorem. What is the sum of the degrees, the total degree, of the vertices in the graph depicted below? So let's just count the edges. There's 1, 2, 3, 4, 5, 6, 7, so 14. There are 7 edges between these, 5 vertices. So the total degree will be 14. Now if you want to verify this, go around and add up the degrees. 2 plus 4 is 6, plus 2 is 8, plus 4 again is 12, and then plus 2 is 14. So you see again here the theorem is holding again. The number of edges doubled is the total degree. All right, and then which of the following statements describes the inductive step? Well, they describe that up there, right? Start with a graph. If you do induction on the number of vertices, you start with a graph and remove a vertex. Assume the theorem holds for a graph with the vertex removed, and then prove the theorem holds when you put it back when you have one more. Right? And then there's some applications of graphs, uses of graphs in certain fields. I'll let you read those. All right. So here, constraint graphs, graphs for scheduling. So say we consider the set of classes and their corresponding times. So class A is held Monday, Wednesday, and Friday, runs from 3 p.m. to 5 p.m., and so on. Two classes conflict if their meeting times overlap. So number one, which of the following graphs correspond to the constraint graph for the set of classes? So remember that we'll say that there's a conflict. We'll put an edge between them if they overlap. Right? Yeah, see, there's an edge between two vertices if the corresponding courses have a conflict. All right, so how about class A and B? All right, so you got four vertices for each class. Do class A and B conflict? Well, yeah, they meet Wednesday. This is 2 to 4, 3 to 5. There's an overlap there. So there should be an edge from A to B. A to C as well, right? They both meet on Friday, and there's an overlap, 5 p.m., 4:30 p.m. So there should be an edge from A to C as well. And also from A to D, because, Monday, Wednesday, Friday they meet, and 2:30 to 3:30 interferes with the 3 to 5. So there's an edge from A to B, from A to C, from A to D, because they all interfere with each other. Right, how about from B to C? Well, they meet on different days, so there's no edge from B to C. And how about B to D? Well, yeah, there's an overlap there. So there should be an edge from B to D. And then from C to D, they meet at, Friday, sure, but they meet at different times. There's no overlapping. So A to everything, and B to D. This one here gives me all the edges with the conflicts. All right. So this last part of the section is on some common graphs. They're so common, they're given special names, they're given special symbols to represent them. So some graphs with special structure, right, are given their own name and notation because they come up frequently in graph theory. The figure below shows some more common examples. So you see this K here. Now I know it's weird, but they use C for something else. K is called a complete graph. K, I guess you could say K for complete, even though complete begins with a C. And the subscript just tells you how many vertices there are. All right, now a complete graph means that every vertex is adjacent to every other vertex. So in a K6 here, see all 6 vertices are adjacent to the other 5. So a complete graph is a regular graph. Every vertex has the same degree. And the degree is going to be 1 less than the number of vertices, because again, every vertex is adjacent to every other vertex. So K sub n is called a complete graph on n vertices. K sub n has an edge between every pair of vertices. The figure shows K6. Right? Now K sub n is sometimes called a clique of size n, or an n-clique. And as I mentioned, every complete graph, Kn, is an n-1 regular graph. every vertex will have degree 5 or degree n minus 1. This graph in the upper right corner with the C7. This is a cycle on 7 vertices, just one big, basically a circle. Just go around and around, and every cycle is 2 regular. See how every vertex has a degree of 2? So every cycle is 2 regular. Right? So Cn is called a cycle on n vertices. The edges connect the vertices in a ring. Right? And like I said, every cycle on n vertices is 2 regular. This Q graph here, where every vertex is labeled by a bit string with 1s and 0s, this is called a hypercube. And this, this subscript is on, bit strings of that length. You see how every single label of the vertices here is a bit string of length 3. Alright, so sorry I had a phone call there. I apologize. So these Q3s are hypercubes. Again, the vertices are labeled with bit strings of that length, the subscript. So you see I have 8 vertices here, and 2 vertices are adjacent only if the bit strings differ in one position. So you see how 0, 0, 1 and 0, 1, 0, right, those only differ in the second position. So they have an edge between them. And you see 0, 1, 1 and 1, 1, 1, those only differ in the first position. They have an edge between them. So it's just changing one bit. Right? So if you take any bit string, just change one bit from a 0 to a 1 or from a 1 to a 0, and you get another vertex that you're adjacent to. Right? And these are called n-dimensional hypercubes. Right? This is a 3-dimensional hypercube, aka a cube. And you can see a cube here. But this is also good in 4 dimensions, 5 dimensions, right? And you can't really picture those. Alright, right. Then this last graph. Now I know I said, this is also called a complete graph, but it's a complete bipartite or 2-part graph. They call it a bipartite graph. Now the K with the 3, 4 here as a subscript means that one side has 3 vertices, the other side has 4 vertices, and each of the 3 vertices is adjacent to all the 4 vertices. And vice versa. All 4 vertices on the right are adjacent to all 3 vertices on the left. And they're kind of kept separate because, the 3 vertices on the left, none of those are adjacent to each other. And the 4 vertices on the right, none of those are adjacent to each other. They're only adjacent to the set of vertices across. All right. So this has n plus m vertices. The vertices are divided into 2 sets, one with m vertices, one with n vertices. There are no edges between vertices in the same set, but there is an edge between every vertex in one set and every vertex in the other set. All right, so like I was saying. Alright, so a complete graph on n vertices, a cycle on n vertices, a hypercube of n dimensions, and a 2-part graph or a complete bipartite graph. Alright, so let's ask you here, this one here says 5 vertices, every single one has degree 4. This would be a K5. A complete graph on 5 vertices, right? Every vertex is adjacent to the other 4. B is one of those cycles on 5 vertices, and every single vertex has degree 2. So that's C5. Right? It's a cycle on 5 vertices. This one, you got a set of 3 vertices that aren't adjacent to each other, a set of 2 vertices that aren't adjacent to each other, and then every vertex in one set is adjacent to the vertices in the other set, and vice versa. So this is one of those complete bipartite graphs, a K3-2 or a K2-3. And then of course, the D looks exactly like B, but with an extra vertex, is a cycle on 6 vertices. All right, then the challenge activity. What is the grass vertex set? Easy. And the edge set. And don't forget to put, set brackets. Put braces instead of parentheses, right? And put commas between values and stuff like that. They'll give you examples here. That should be pretty simple. Vertex set and edge set. What are the neighbors of vertex C in a list? What is the degree of vertex C? What's the total degree of the graph? Now again, you can count all the degrees or just count the number of edges and double it, and that'll be the total degree. And finally here, they have a, you can't see when I scroll this down, but it's like which, you're filling in a letter here, so like this would be a cycle on 6 vertices, right? C6. And this one's a complete graph on 5 vertices. And this one's a complete bipartite graph on a set of 2 vertices and a set of 3 vertices, right? The K with the 2, 3. Let's do that one at least. Right? And that's it. All right, so lots of definitions. Okay. Then you have your additional exercises. Right? Some of these are assigned, not all of them maybe. I don't know. I don't remember what I assigned, but if something isn't assigned, I would still recommend looking at it, just to get more exposure, get more practice. And you also have the solutions to look at if you need. Right? But don't look at the solutions until after you've tried to work it out on your own. All right? If you're just looking at solutions straight away, you're not going to really learn much of anything. Okay. Right, and hopefully this video was a reasonable guide for you for this section. If you have any questions at all, of course, send me a message and I will get back to you as soon as possible. And thank you very much for watching.